Let's have some more fun with analytic semigroups. Now, this all goes back in the end to Cauchy's integral formula, which is right here. So just have another look. 1 over 2 pi I integral over closed loop f of z divided by z minus a is f of a if the loop includes the point a. If the loop gamma does not include the point a, then this integral is 0. And then we define sectorial operators right here. And here you should remember one thing was this definition, right? We have like a sector where we exclude 0. This was called sigma pi over 2 plus delta. And so here on the right is the resolvent set. On the left can also be resolvent set, but at least the sigma is in the resolvent set. And then here's an important estimate. So on this resolvent set, we can estimate the resolvent by a constant m epsilon divided by lambda. And then we used Cauchy's integral formula for sectorial operators. So you take a sectorial operator A, you put it in there, and then you use a strange complex valued integration to define a complex valued semigroup T of Z. And now the argument Z is a complex number. So, in today's lecture, I want to show that this definition actually makes sense. In particular, I'm after the semigroup property. So that T of Z1 plus Z2 equals T of Z1 plus T of Z2. Now, this proof is gonna be some fun. So, in detail, we have ADA, a densely defined sectorial operator with angle delta, and then we take a point Z in sigma delta, so that was a smaller sector. And for this set, we define T of Z as before. And I'm going to show Tz is uniformly bounded for each smaller sector, sigma delta prime. Then the map Z maps to Tz is analytic in sigma delta. And then that's why we call this an analytic semigroup. And then if you have 2 points Z1, Z2 in sigma delta, then you have the semigroup property. And it's strongly continuous as Z maps to T of Z. Let me remind you about all these sectors which play a role here in this little figure. So complex plane, C. So this was a sector which defines a sectorial operator, sigma pi half plus delta. So it opens up a little bit more than pi half. And then typically the spectrum of the operator would be sitting somewhere here on the left, maybe some individual point spectrum values as well. Now we define the analytic semigroup on a smaller sector, so here and here, sigma delta. And then we show that this is analytic, this is uniformly bounded in an even smaller sector. Let's change the color, so then I have an even smaller sector, which is a bit difficult to plot. Okay, so sigma delta prime less than delta. Okay, so in this thing, we then have a uniform estimate. And in the green small sector, we have that Tz is well defined. Starting with the resolvent. So I represent the resolvent as the Laplace transform of the semigroup. Remember, this was one relationship in our triangle of semigroups. Now the right-hand side, so the lambda only appears here. So this is definitely analytic. So the map lambda maps to e to the lambda z resolvent of A is an analytic map whenever the resolvent exists, and so this is certainly true in the sector pi half plus delta minus a little bit. But this means if you have an analytic function, if we integrate over it, like in the definition of the Cauchy integral formula, the choice of path doesn't matter. And so what we can do then, for our definition of the semigroup, we can choose a very particular path, and this very particular path is called gamma r. And this gamma r consists of 3 parts, gamma r1, gamma r2, and gamma r3, where r is a positive value. Okay, so this cries out for another picture. What I do is look at gamma 2r first. So what I have here, I have radius times e to the I alpha. Alpha is an angle. And the angle goes from an angle minus pi over 2 plus delta minus epsilon to another angle plus the same thing, pi half plus delta minus epsilon. And it has a fixed radius r, so it's part of its circle. It is part of the circle going around like this, where you have a minus pi half plus delta minus epsilon here, and you have plus so and so right there. So this would be gamma r2. And now gamma r1, let's look at gamma r1. So then we have a fixed angle here, which is the lower limit angle, so it is this angle there. But then the radius goes from minus infinity to minus r, so this goes actually this way. Okay, so this would be gamma r1. Now yeah, and then gamma r3, again the radius then goes to plus infinity, whereas the angle is the angle, so then this goes this way. Gamma r3. Now it is about to estimate the semigroup defined by the Cauchy integral, so we want to do estimates on each of these bits individually. So gamma r1, gamma r2, gamma r3. We also do this for the smaller sector here. So let's plot this again, sigma delta prime, and we take a z sitting right in sigma delta prime. So this is this guy. And then we set the radius to be 1 over z. So we make a relation between the point z and the radius of this path which we are choosing. Okay, let's start on gamma r3. So we take a mu right sitting there somewhere. In the integral we have to deal with the term mu times z, which we can write in polar representation as the absolute value of mu z, and then the angle argument of mu plus the argument of z. And now I would like to change to estimate this argument exponent there. Okay, let's see how we do that. So the argument of mu is on the line gamma r3, so it has exactly the angle pi half plus delta minus epsilon. Now epsilon was chosen to be equal delta minus delta prime over 2. So here I say epsilon is a half delta minus delta prime. So that's what I subbed there. And then I can work the delta with the minus delta half, so then I get pi over 2 plus delta prime over 2. So I'm here. Now the argument of z, though, is less or equal delta prime. That was the smallest of all the sectors. So which means the argument of mu plus the argument of z is this one of mu is larger or equal this minus the maximum amount z could have. And then if you work this through, there must be a 2 here. Then this comes out to be pi half plus epsilon. So the argument in the exponent is bigger than pi half plus epsilon. On the other hand, we can again take the value for mu and then add the value for z, and then we get an upper bound. And now I estimate delta with pi over 2 and delta prime with pi over 2, and all this together gives 3 pi over 2 minus epsilon as an upper bound. So this means that the sum argument of mu plus argument of z is between pi half plus epsilon and 3 pi halves minus epsilon. This means that the cosine of this, which is the same as 1 over the absolute value real part of mu z, so that's the cosine. This is bounded by the cosine of pi half plus epsilon. In this interval the cosine is decreasing, so we take the largest value there. But this is minus sine of epsilon. So minus sine epsilon is an upper bound for the real part of mu z divided by the absolute value of mu z. So then we can say e to the mu z absolute value is bounded by e to the minus mu z sine of epsilon. Okay, so this is actually really rather technical, but on the other hand is basic complex analysis. Okay. So what do we do with this? Then we sub it here, so then I multiply the e to the mu z, which we just estimated, with the resolvent. For the resolvent I have the estimate m epsilon divided by mu, and then this bit with the sine epsilon is the same thing we just did. We did this for gamma r3, but we get a very same estimate for gamma r1. Can do the very same construction. Good. So then we have done gamma r1 and gamma r3, so now we need on to gamma r2, where we have a fixed radius, and if mu is on that set, it has a radius r, which is 1 over z. So meaning that mu times z is equal to 1, so then the e to the mu z term is e to the 1, so that gives us an e here in the estimate. The resolvent again is estimated by m epsilon over mu, which comes from the definition of a sectorial operator, and 1 over mu is the size of z, so then we get this estimate there. So then together, putting all three things together, gamma r1, gamma r2, gamma r3, which means we sum over all these gamma rk's over all these expressions. So I just collect what I had earlier. So here the sine epsilon term, which came from gamma r1 and gamma r3. And now we integrate this over a row. We get 2 of them, right? So then we get a 2 here. And then this other term with the e in front comes from gamma r2. And now we integrate this between fixed angles over the fixed radius, d alpha. And now this is an integral which does not depend on alpha, so we can just integrate it out and get 2 pi e m epsilon. For the first integral now we do a substitution. We substitute rho of z for rho, and then this becomes an integral from 1 to infinity, 1 over rho e to the minus rho sine epsilon d rho, and then this term with the 2 pi e m epsilon. And all this is uniformly bounded. That's what it's all about. This is all uniformly bounded and independent of the choice of z. Should be noted it does depend on delta prime through the choice of epsilon, because this epsilon appears in the sign and in the m epsilon. So there's a dependence on the delta prime, but otherwise it is a uniform bound, and we prove item number 1. Item number 2 would be the analyticity in z. This is rather easy because the map z maps to e to the mu z resolvent mu is analytic. So then the integration, the path integration, is also analytic, and we have item number 2.